Okay, so in this discussion, I'm going to go over the difference between thermal heat, or thermal energy and temperature, and then we'll look at how heat is transferred through conduction, convection, radiation, and then a little bit about the electromagnetic spectrum and sort of how it's all interrelated. Okay, so first of all, temperature is a measure of the average kinetic energy of the molecules of a substance. So something that is quote unquote hotter has more kinetic energy. So if you remember, if you look at the molecular level of any substance at all, the molecules are going to be vibrating, right? And so a higher temperature means those molecules are vibrating more, right? So this goes for anything. So if I have there's a pen here, I think you can see it. So the molecules of this pen are vibrating. If I would, hold a lighter into or hold it over a stove that's, an open flame, it's going to warm up, right? And as this pen warms up, those molecules vibrate more. That's what temperature is, right? And so as those molecules vibrate more, it has a higher temperature. And consequently, it's also going to radiate more energy as well as you increase the temperature. Okay, so that's what temperature is, a measure of that sort of average of the whole thing. And so more overall energy with the same substance, you're going to increase the temperature. Whereas heat is the total energy, not the average, but the total energy of the substance. And so you can have more heat, more total heat, by either increasing the temperature or increasing the size. So for total thermal heat, it's not just how hot it is, but how big it is. And I'll give you a good example of that here. So if you look at the bottom right, you see, we'll call this a gallon of boiling water, so it's about 212 degrees, and then a giant iceberg, which is about 32 degrees. So if you think about it, which of these has a higher temperature? It's obvious. The boiling water, way hotter, well over 100 degrees, close to 200 degrees hotter, or more temperature than the ice. However, in terms of more heat, the iceberg certainly has more heat, because even though the average energy is not that great, it's not vibrating that much relative to this hot water, there's so much ice that has way more total heat. And that's kind of a good way to think about the difference between heat and temperature. Okay, so the total heat is just the total energy, right? And even something that's cold has a lot of heat. That actually becomes important when we look at HVAC later on, where you have relatively cold air outside, but you can still pull heat from it in order to operate a heat pump, for example. We'll talk about that in more detail. But remember, temperature means more vibrational energy, which means more radiant energy as well. And then just a quick look at temperature scales. So on the left, we have a comparison between the Fahrenheit, the Celsius, and the Kelvin scale. We don't deal in Kelvin or Celsius, but it's important you understand the basics of them. So what I want you to know is that, again, temperature is based on this vibrational energy. And so as you heat something up, the molecular vibration increases. The molecules actually vibrate more. And that's what you're doing when you add heat to it. It actually converts that thermal, however you're providing it with that heat. That heat goes into the substance and then causes the vibration to increase. Right, so some things I do expect you to know are that the boiling point of water is 212 degrees Fahrenheit or 100 degrees Celsius. The freezing point is 32 degrees Fahrenheit or 0 degrees Celsius. That's important to know. And the temperature scales are just an FYI, are based on pure water at atmospheric pressure, so like sea level pressure. And things change a little bit when you go to high elevation or high pressure. And if you have some impurities in the water, that changes things too. But anyway, that's how we measure temperature. So again, higher temperature means more molecular vibration. More vibration also means more radiant energy. In terms of Kelvin, the important thing to understand about Kelvin, and here's really what you need to understand, is that 0 Kelvin is absolute zero. So absolute zero is the theoretical minimum temperature. It's defined as the temperature at which all molecular motion stops. Okay? And so the Kelvin scale was created to do sort of like physics experiments and so forth, because it's an actual absolute scale. In other words, the bottom of the scale, which is 0 Kelvin, is the absolute minimum. You can't get any colder than that, because that's the temperature at which all molecular motion stops. And so remember, the temperature is a measure of that molecular motion. 0 Kelvin is when there is no motion. All that energy is gone. So that's an absolute zero. That's why it's called absolute zero, because you can't get any colder than that. I mean, if a temperature is a measure of vibration and you have no vibration, you can't get smaller than that, right? And so that's an actual 0 point. Whereas the 0 degrees centigrade and 0 degrees Fahrenheit, they're not actually the minimum possible temperature. Obviously, I mean, we've all seen negative of both in our lives. So 0 is not the absence of temperature in the Fahrenheit and Celsius scale, but it is in the Kelvin scale. Okay, and so all I really need you to know there is that at 0 Kelvin, all molecular motion stops, and that's called absolute zero. Okay, and so anything above that temperature is vibrating. Anything above that temperature, again, is radiating, which for our purposes is everything, because this absolute zero is only theoretical. We've never actually seen it in the real world. It's just defined as when molecular motion stops. So for our purposes, everything around you is vibrating, and everything around you is radiating energy, as we've discussed previously. And speaking of radiating, I don't expect you to know this whole electromagnetic spectrum. I just want to give you a sense of how it works. So remember, anything above absolute zero radiates. The hotter something is, the more intense the radiation, which means the shorter the wavelength, right? So here's the short wavelength up here, and then longer and longer and longer wavelength here. So you got like microwaves are really long. They're a couple of meters long. And wavelength, if you think of radiation, again, remember, radiant energy goes in waves. The wavelength is just the distance between the peaks of the wave. That's it. And so the hotter it is, the shorter that distance between those peaks, the more intense the radiation, right? So you have like your X-rays and gamma rays, stuff that that can sort of like penetrate or are very dangerous. Whereas this is, we have our radio waves and microwaves and so forth. They're really long wavelengths. The other thing that's good to know is that the sun emits mostly visible radiation, which is in this little sliver here. It's on the order of 200 to, I think, 800 nanometers. Anyway, you don't need to know that. The point is, that's where the sun emits most of its radiation. Whereas people and the stuff around you is almost entirely emitting this longer infrared wavelength. Okay? So remember, the hotter something is, the shorter the wavelength. So the sun's really hot, so it's emitting this really short wavelength. And then stuff around you, people and the table and the building around you, whatever, that's not as hot as the sun, obviously. And so that's over here on the longer wavelength side of things. Okay. Okay, so finally let's talk about how heat is transferred between substances. This is really fundamental and important to understand. So make sure you understand these three processes. Okay, so heat is transferred, as we discussed, energy and heat are transferred around you all the time. And there's three ways. There's only three ways that can actually be transferred from one thing to another. Number one is conduction. So conduction is direct physical transfer. And we'll go over each of these in a little more detail. Convection is heat that travels with the fluid. And then radiation is that electromagnetic energy that we've talked about a number of times. So conduction is, remember, when you heat something up, the molecules vibrate, right? So again, let me take my pen as an example. If I heat this up, it gets really hot, and then I put my hand against it, okay? So my hand is colder than the pen, and so that pen has more vibrational energy than my hand because it's hotter. So what I feel as a hot pen or a hot object is just that vibrational energy transferring to my hand. And so if I do that and I take my hand away, my hand's going to be warmer because it pulled thermal energy from that pen, right? I could do the same thing at a table or like a cold window. Put your hand against a cold window, and now the thermal energy is going directly from my hand to the window because it's going from the hotter hand to the colder window. Here it's going from the hotter pen to the colder hand. So heat always travels from higher to lower temperature. So that direct physical contact, that's conduction. It's molecules actually bumping up against each other and giving one or the other kinetic energy. In this illustration here, the conduction is actually through, right? So we have a hot fire and then a metal poker, and the conduction is actually conducting through the metal here. So conduction, again, doesn't mean it doesn't have to be between two different objects. It can be within a single object. And if we have this, what happens with the poker is this end gets hot, and then eventually this is going to get hot as well. But it's not because the heat travels over here, like underneath and whatever. What happens is this gets hot, and then this bumps into these little molecules here. That gets hot, and then that gets hot. That gets hot. That gets hot, and so on. And the heat traveling up is traveling up through conduction. Okay, so conduction can happen between two or more things or within one thing. And if you think about like the handle of a pot on a stove, same thing happens, right? Eventually it's going to get hot, and that's through conduction. Convection is heat traveling with the fluid. So in this example, we have hot air rising. That's really common. That's actually convection, and that's because air is actually a fluid. Okay? So this can happen with water, it can happen with oil, or whatever. The most common way we see convection is through the air, and this is like what drives the weather systems and a lot of heating systems and so forth. But air is a fluid, and when you have convection, you have warm air rising and moving with the air, okay? And it takes that air somewhere else. And then finally, we have radiant energy transfer, which we've talked about a number of times. Again, everything around you is radiating energy, and it's radiating in all directions. When that radiant energy hits an object, it's going to absorb, or some of it's going to absorb, and it's going to warm it up. Right? So in this example, we have a hot fire, and you're standing to the side of it. That sideways energy is not convection. It's not warm air rising, right? That's going up. That's warm air, or not warm air. That's radiant energy traveling away from the fire, hitting your hands, and when it hits your hands, it warms up your skin. And that's the same thing as sunlight outside. You step outside, your skin gets really hot. That's mostly from the radiant energy of the sun hitting your skin. Okay, so remember, everything around you is radiating all the time. So those are the three ways that heat is transferred: through conduction, convection, radiation, and that's very important to understand because it's a very important part of maintaining energy in a building. So I expect you to understand these moving forward. Okay, so in this presentation, again, we went over the difference between heat and temperature. We looked at how heat is transferred and then looked at the basics of the electromagnetic spectrum.